So in this video, I want to talk about the conservation of energy. But let's say we have this rubber ball. Something important to note is this rubber ball, due to its location and distance from the Earth, it has a certain amount of gravitational potential energy. However, if we were to lift this ball upward, let's say we lift it upward 10 meters into the sky, so now the ball is up here, we know now due to its location, it has gained some gravitational potential energy. However, how much gravitational potential energy has it gained if we moved it 10 meters up in the sky? Well, we can solve that change and that gain in gravitational potential energy using this equation. Mass times gravity times height. And again, we know the mass of the ball is 10 kilograms. We know the mass is 10 kilograms. We know g is the acceleration due to gravity, which is 9.8 meters per second squared. But for simplicity, let's say it's 10 meters per second squared. And this height represents that change in height, how much distance it traveled. So this height in this situation would be 10 meters. So now we could solve this with some simple math. We could solve this would give us 1,000 joules. So now we know this ball has gained 1,000 joules of gravitational potential energy. But something important to note is this equation, it's not telling us that this ball has 1,000 joules of gravitational potential energy. That's not what this equation is saying. This equation is used to find how much the change in gravitational potential energy. This ball relative to this position has gained 1,000 joules of gravitational potential energy. That's what this equation tells us. It tells us how much the change in gravitational potential energy. It doesn't tell us the absolute amount of gravitational potential energy. It tells us how much it gained. And we know the larger the height traveled, the more gravitational potential energy it gains. Because the larger the height traveled, the larger this h, the larger this value, and the more gravitational potential energy it's gained. So what this equation is telling us is the amount of gravitational potential energy it has relative to this initial point is it gains 1,000 joules of gravitational potential energy. However, where did this energy come from? We know from the conservation of energy is never just created or destroyed. We know that energy comes from somewhere. It can't just pop out of nowhere. It can't just come from thin air. We know that energy has to come from somewhere. So where did this energy come from? Well, we would have to do some work. We would have to take our hand. Or our paw, I guess, but we would have to apply some kind of force and apply a force upward. We would have to apply that force and we would have to do that work. We would have to do that work on this object, moving it upward. So we would have to do that work. We would have to impart that force and that energy on this and do work on this object, lifting it upward. So now it's gained that energy. And that's where that gravitational potential energy comes from. That energy just doesn't come from nowhere. It has to come from somewhere. So that's where that energy came from. So now we have this ball up in the air. But now, what if we had this ball? What if we were to let it go? What if we were to let this ball go? Now it dropped downward. And let's say dropped, so now it starts accelerating downwards. It feels that force downward, and now it starts accelerating downward. So now let's say it's at this point. Now it's at this point. And again, it's still a 10 kilogram ball. That doesn't change. But now how much gravitational potential energy does it have relative to this initial point? Well, again, we can simply solve it. Mass times gravity times height. And now let's say this height, happens to be 4 meters. So now at this location, how much gravitational potential energy does it have relative to the initial amount? Well, again, we know mass is just 10 kilograms. We know g is just 10 meters per second squared. And we know this time the height is 4 meters. So now the height is 4 meters. So again, if we saw this, we would get 400 joules of gravitational potential energy. So now the ball has 400 joules of gravitational potential energy. Another way we could have done this is we saw that this difference in height must be 6 meters. So we could see this distance must be 6 meters. Because if this was 10 and this is 4, we know this must be 6 meters. So again, using mgh, remember this equation tells us the change in gravitational potential energy. So this difference in location, that height would be 6 meters. G is still 10 and mass is still 10. So this would give us 600 joules. So this tells us that change, how the change in gravitational potential energy, which we see is 600 joules. So those are two different ways you could solve this. But again, remember, the point is that this equation tells you the change in gravitational potential energy. So now we know the change relative to this initial location is 400 joules. But now you might wonder, if initially we had 1,000 joules of gravitational potential energy, now the ball drops, now it has 400 joules of gravitational potential energy, where did that 600 joules of gravitational potential energy go? We know energy is not created or destroyed. We know that 600 joules isn't just destroyed, it just disappears. So where did that energy go? If we initially had 1,000 and now we only have 400, where did that 600 joules of energy go? Well, we know if we drop this ball, we know this ball is moving. We know this ball is moving. It has an acceleration downward, so it's moving with a velocity. So we know it's moving with a certain velocity. And something important to note, whenever an object has mass and velocity, so whenever there's an object with mass that has a velocity, so whenever there's an object with mass and it's moving with the velocity, then we know it has kinetic energy. And that's always true. Every object with mass that has a velocity that's moving has kinetic energy. And the formula for kinetic energy is actually 1/2 mv squared. So any object with mass that has a velocity has kinetic energy. So this ball is moving. This ball is moving, so therefore it must have kinetic energy. This ball must have kinetic energy. How much kinetic energy? Well, it must be 600 joules of kinetic energy. And that explains that this ball now has 600 joules of kinetic energy. And again, we saw it had 400 joules of gravitational potential energy. Now we know in total that's 1,000 joules. And that makes sense because we know initially we had 1,000 joules. So we know if this initial time period we had 1,000 joules, we know it must still have 1,000 joules in total because we know that energy isn't created or destroyed. So what happened was just 600 of those joules were converted into kinetic energy. And what was left were the remaining 400 joules of gravitational potential energy. So the initial amount of energy equals the final amount of energy. So now we know this ball must have 600 joules of kinetic energy because we know it has 400 joules of gravitational potential energy, and we know in total it must have 1,000 joules because again it initially had 1,000 joules. So now we know the kinetic energy of this ball. And again now we know the kinetic energy is 600 joules. So now we know the mass is 10 kilograms. So now we could solve for the velocity with some algebra if we were interested. So that's the conservation of energy. So now I just want to do one last example to really illustrate this. So let's say we had this initial situation where we had this ball. And let's say we had the Earth, and let's say we had this ball. And again, let's say we were 10 meters up in the sky. And let's say again it was a 10 kilogram ball. Then we explained the amount of gravitational potential energy relative to this initial location was 1,000 joules of gravitational potential energy. So we know if we took a snapshot picture of these initial conditions, we know the energy total, or the initial energy, the total initial energy was 1,000 joules. It had 1,000 joules of gravitational potential energy, and all that energy was in the form of gravitational potential energy. So we take a snapshot picture. And we see the total amount of energy. Now what we do is we let that ball drop. Now we let the ball drop, and now it's dropped. And now it's dropping, let's say it's at this location. Which let's say is 7 meters above the ground. So something important to note. We took a snapshot picture. In the initial conditions, we had a total amount of 1,000 joules of energy. So therefore, we know if we took a snapshot picture at this instant in time, we know the total amount of energy must still be 1,000 joules of energy. So the energy final must still be 1,000 joules of energy because energy is conserved. If we started out with 1,000 joules, we know 1 second later, or 2 seconds later, or 1,000 seconds later, the total amount of energy must still be 1,000 joules because energy is conserved. Energy isn't created or destroyed. It's just converted from one form to another. So that's how I like to approach these problems. And again, if we solve now the gravitational potential energy it has relative to this point, again, just mgh, but we know now h is 7. If we solve this, we would get 700 joules of gravitational potential energy. So we know this ball has 700 joules of gravitational potential energy. But we already determined that the total amount of energy must be 1,000 joules of energy. We know the total amount of energy must be 1,000 joules. So if we have 700 joules in gravitational potential energy, therefore we must have 300 joules of kinetic energy. Because now that's the only way for our total amount of energy to equal 1,000 joules. So that's how I like to solve these conservation of energy problems. What I'd like to do is I'd like to look at the initial conditions, and I'd like to take a snapshot picture of the initial conditions and find the total amount of energy. Now I know in the final conditions, the total amount of energy must be constant. That energy is conserved, so the total amount of energy must still be 1,000 joules. So therefore, I can use some algebra and I can solve. If I know the mgh, the gravitational potential energy, I could solve what the kinetic energy must be. Or if I knew the amount of kinetic energy it had, I could determine what the gravitational potential energy it must have had, so therefore I could determine where the location was, the height of the object. So that's how I like to solve these conservation of energy problems.